Okay, so far we talked about feedback, and we talked about how we can analyze feedback and understand the system theory. We saw that we can use the return ratio and the asymptotic gain formula to determine the transfer function in terms of the three parameters. And then we saw that we also came up with a loop gain, which was an invariant for a single loop. So basically you could cut the loop anywhere you want. You were not limited to doing it right at the source. You could do it anywhere you want. And the way we did it is that basically we said that if you have a unilateral loop, your overall loop gain, 1 over your overall loop gain is equal to the sum of the 1 over the voltage loop gain, which is when you cut the loop and leave the other side open, apply voltage in the forward direction, plus 1 over the current loop gain, which is basically when you apply a current source and short the other end and see what current comes back. And we saw that this is for unilateral loop, and if you have a bilateral loop, what happens is that then you have a third term, which is a correction term, which will be defined in terms of the reverse loop gain. We need to determine one of the reverse loop gains, and there was a relationship between these 4 loop gains, the forward voltage and current loop gains and reverse current and voltage loop gains, which was that the product of the forward and reverse voltage gain, loop gains, is the same as the product of the forward and reverse current loop gains. And that's always true. So what happens is that you have something like that, and then you can calculate that there's a correction term for bilateral. Anyway, so we determined this. We saw this is nice and good. But now, today we will start talking about what are the implications of applying feedback, and particularly in terms of stability. So the question we will be talking about today is stability. So we'll talk about this, and we'll continue talking about it next time, and what are the general criteria for stability and how you can deal with it in circuits and all that. But my first question is, let's go back to the basic. Why did we apply feedback? Why did we intentionally apply feedback to a circuit? What were the advantages of feedback?
Increase gain bandwidth.
One was increasing the bandwidth. The other one was that you basically made the gain or the transfer function less dependent on the parameters of your amplifier as long as you had high enough gain. You said, if I can make my gain high enough, then what happens is that I can make it independent by applying feedback to a network which is typically passive, not always, but typically, and you've seen some cases of active feedback, like cherry curve, but typically passive, so it depends on a few small parameters. Usually you want to make it such that it depends on the ratio of 2 resistors or 2 capacitors. So it's less dependent on the parameter variations, temperature variations, things like that. So it's in a way making it desensitizing your overall transfer function to the forward. So that was another advantage of feedback. And then what are the other advantages? So you had also linearization. That's probably the most fundamental thing, desensitization of linearization. You saw that if you had nonlinearity in the forward path, you can actually linearize it and make it more linear. So, and we saw that this improvement got better. I mean, you got more improvement with increasing the amount of feedback you had. And what was the measure of feedback you had? Is the loop gain, right? In the system perspective, in the system picture, if you go back to this like high-level system, which needed to be really rethought in the context of circuits, the transfer function, we saw easily that we had calculated this multiple times before, and I'm sure everyone has done this before, is this. And we said this is really loop gain. It's really negative loop gain. Because loop gain is minus AF if you go around the loop. But we saw that this is loop gain, and basically if you look at this quantity, we said that the higher this quantity, this loop gain, is, the closer you will come to the ideal transfer function. So actually a better way of writing this, as far as the circuits are concerned, is this. If you multiply and divide the numerator and denominator by f. So, and then remember that 1 over f, when we did the first lecture, the asymptotic transfer function. So another way of thinking about it in terms of a circuit is like this. If you have something like this, which is unilateral, there's no reverse path through here, basically that second term doesn't exist, that H0 term, because H0 is going to be 0, because there's no way for a signal to parasitically go through this. So this basically is another way of saying this in this context. So in this context, T and loop gain, and we won't make a differentiation between the loop gain and the return ratio because this is a system level thing, so they will be the same. So I'm going to show it this way. And when your T becomes very large, then you're independent of that and you're only dependent on H infinity, which in this case is going to be simply 1 over F. So your feedback return is a property. So these are the basic properties of various basic properties of feedback we've seen before. Okay, so it seems from this that if you want to get a better result, the more T you have, the better off you are, right? If T goes to infinity, this becomes ideal. So is there a problem with doing that? Well, let's find out. So what we will do today, I'll start with an example. Instead of doing an abstract thing first and then going to examples, let's start with an example. But this is an example supposed to be illustrative of a lot of things that are important and happen. To show you several things. So, as an example, let's start with a 3-stage amplifier. 3-stage common source amplifier. So let's say your input is a current source. You have some source resistance Rs. You have some input capacitance. Let's say your source has some capacitance. And then you go to the transistor. You have a 3-stage amplifier. Very simple common sources. And then you have a follower on the output. Bias with an ideal bias, an ideal current source. So this is, let's say, M1, M2, M3, M4. Now this, and let's say for now, we'll assume only, we consider only the CGS capacitance of these transistors. Let's just consider that to make it simple and chapter. So let's say you have the CGS of this guy, CGS of this guy, CGS of this guy. And then in this case, we know that the CGS of this transistor is not a substantial factor anyway in a follower. Why? Because if the follower has a unity gain, you remember that there was 0 very close to the pole. And another way of seeing it is that it's a Miller effect, right? These two sides go up and down together. The gate and the source. The source follows the gate. So they're going up and down together, so this capacitor experiences very small voltage swing. So its impact is really diminished. So let's not worry about that. So let's consider these capacitors. And we easily see these two capacitors are in parallel. So we lump them into one capacitor. So which contains some of the capacitance of the source and some of the capacitance of the first transistor. Now, this source, by the way, is a good representation, for instance, of a photodiode in optical communication systems. A photodiode can be represented as its photocurrent is a current source in parallel with the capacitance of the diode itself. And there's a trade-off there, where basically if you make the surface of the photodiode small, what happens is that the photodiode will have less sensitivity, but it will have smaller capacitance. And if you make the surface very large, you will have more sensitivity, you generate more current for the same amount of intensity, but you will have larger capacitance. So overall, bottom line is that you have a capacitor here, which is the combination of these two. Let's call it Cin, C1, and C2. So it's split. Cin, C1, and C2. Stay consistent. So at this point, this is an open loop amplifier, right? It's a transimpedance amplifier, really, because it's an input voltage, input current to output voltage. What is its gain? Or more accurately, what is its transfer function or transimpedance at low frequencies first? So
do you have more R1?
Okay, so let's go in steps, right? So first we have to convert this current to a voltage. So GM1R1 minus GM2R2 minus GM3R3, and what is the DC gain from here to there? 1, right? Because you have the current source, it's exactly what? 1. But yeah, so that's what it is. So let's say, and this is really a transfer function, but it has units of ohms. So you can show it an H or Z. So let's show it as Z. So Z, 0, basically. You can basically show it as Z of S. So this is Z of S, which would be Z of 0 times the dynamics. So, and Z of 0 here is, we just determined it to be, there are 3 minus signs, so there's one left. There's minus RS times GM1R1, GM2R2, GM3R3. So the question is, how many poles, how many zeros? Now we should be experts in this. Right? So, and this is a trivial example. What can you say about this? You can say very quickly, a lot about this. Basically, you can say everything about this.
3 poles, no zeros.
3 poles, right? You have 3 independent degrees of freedom. No zeros. Why no zeros? Because there is no capacitor shorting of which results in a non-zero transfer function, or any combination of them. So what happens is that, so there's no zeros, so we know this is like the 1 in the numerator. 3 poles. There's one more thing we can say actually about the poles in this example. This is a contrived example. Make it as simple as possible here so we can focus on the other aspects of this thing.
They're all uncoupled.
They're uncoupled poles, right? Because shorting or opening of this one doesn't change the time constant seen by this one. And same here, same thing here. So there are 3 independent time constants, which means that we have 3 poles in this case. So basically the transfer function is really 1 plus tau in S, 1 plus tau 1S, 1 plus tau 2S. So it can be factored like that. Okay? So this is the transfer function. So I can just be more compact. And it's alright. So fine. If I look at the transfer function of this thing, it has 3 poles, 3 left half-plane poles, no zeros. So what do I expect to see in the Bode plot of this thing? If I were to look at the transfer function, so this is basically magnitude of phase of Z, which is the transfer function, because it's an impedance. So what do you see? You have 3 poles, 1, 2, 3, one of them will happen first, and then second one, and the third one. So you have something that starts off at Z of 0, and then starts dropping at 3 dBs per decade. 20 dB per decade. And then 6, and then minus 20 dBs per decade, and then minus 40 dBs per decade, and then minus 60 dBs per decade. So you have one slope, another slope, another slope. And then how about the phase? These are left half plane basic poles. So basically they just constantly drop the phase. So you go from through 3 steps up. This is minus 90, minus 180, minus 270 degrees. If you look at this transfer function, it's a monotonically dropping thing. How do you think the time domain response of this thing looks like? What would you say the time domain looks like? I mean, qualitatively.
No ringing.
No ringing, there's no peaking here, no ringing, there's no complex poles. So it's just some sort of a combination of some exponentials, essentially. So the step response would look like that. Qualitatively. Nothing magical there. Okay, fine. So does it really do that? So let's look at it. If you look at figure 6.2, those are simulation results. So you can see how it looks like. Pretty much you can see the things are smoothed over pretty much from the picture that we've shown, but that's what you see. So the first one is the magnitude plot, the second one you see the phase plot, and the third one is the step response. Now, by the way, what are these time constants? What are these time constants? Let's just write them down quickly. Tau n is Rs, say Cn Rs. Tau 1 is C1 R1, and tau 2 is C2 R2 in this case. The three time constants of interest. Nothing that matters, not out of the ordinary. And by the way, the stuff that you saw are for some numerical values that we picked. So let me just put the numerical values here. So it's a GM of 2 millisiemens. It's a Cin. So a CGS, we are assuming a CGS of 0.5 picofarad and a C, I guess, S of 1 picofarad for the device, for the source itself. So that gives you a Cn, which is the sum of these two, of 1.5 picofarads, a C1 and C2 of 0.5 picofarads. And then an Rs of what, 1 kilo ohm? 1 kilo ohm. And then R1, R2, those resistors of 5 kilo ohms. So these are all 5 kilo ohms. So let's calculate these parameters numerically, see what they are, just to get a sense, and then as we go forward, we'll see what that gives us. So first of all, what is Z naught? What is Z0? Low frequency trans resistance. Well, it's this resistance times these three gains, right? So what are these gains? 2 millisiemens times 5 kilo ohms, 10. 10, 10, 10, 1,000. And 1 kilo ohm, so it's 1 mega ohm. So in this case, numerically, what you have is that you have this, we're running out of space. So Z of 0 on 1 mega ohm, which is like about 120 dB ohms. And then we have, let's calculate the taus. Tau n is what? Is Cn of 1.5 picofarads times 1 kilo ohm, so it's 1.5 nanoseconds. Tau 1 is this the correct one? Yes, picofarad. Okay. Tau 1 is basically 5 kilo ohms times 0.5, so it's 2.5 nanoseconds. And tau 3 is another 2.5 nanoseconds. So we know exactly what the transfer function is in this case, so we can do whatever we want. If you were to calculate the ZBTs, for instance, zero value time constants, do the sum of these three, which would be 6.5, right? Nanoseconds. So if you estimate our bandwidth based on this, omega h estimate, 1 over the sum of the time constant, would be what? Would be what, 1 over 6 point. Yeah. Divided by 6.5. So that's omega h divided by 2 pi. That estimates about 25 megahertz. Right, 24.5. 2 pi is like that. And if you, when you look at your SPICE simulation, so the omega h from SPICE is what? 36.6. So you can see it's conservative. And the reason is that we don't have a dominant pole. So the fewer dominant poles that you have, if you have a lot of non-dominant poles, then you can deviate from. It becomes more and more conservative. But again, it's in the right ballpark. It's about like 30% off. Okay, fine. So that's basically where the circuit stands. There's nothing unusual about it. There doesn't seem to be anything exciting happening yet. So now let's apply feedback. Let's apply feedback. And this is the way we'll apply feedback. So I've designed the circuit to be relatively easy to apply feedback to. So let's put a resistor, RF, from the output lane. So what am I doing? I'm taking a sample of this voltage, really here, I'm in shunt here, if you want to think about it that way, and I'm adding two currents here, which basically makes it shunt. So it's a shunt-shunt feedback. So what do you expect to do? You expect to what to do to the impedance of the input? Lower or increase it?
No.
Lower the impedance of the input, it's shunt, and lower the impedance of the output. So it makes the input a better current meter, because an ammeter is, an ideal ammeter is short, has a zero input impedance, right? So it makes it better in that sense. If you are trying to measure the current, basically more of the current will go in. And also you expect it to reduce the time constant of the input too, if you reduce the impedance here, right, the resistance here. And also at the output, it lowers the impedance, which basically means that it makes a better voltage source. So this is the right kind of feedback to use if you were to make a transimpedance amplifier, something that takes a current in and produces a voltage at the output. So now, by the way, to increase feedback, what do I need to do to RF? Increase it or decrease it? So think about it. If I have no feedback, what is RF? Infinity. So as I decrease RF, I'm increasing my feedback. Right? So with the RF, basically the first thing that we need to do is just basically once you put RF in there, we need to calculate the several parameters for this based on feedback, right? So we know a bunch of things about this. So we can look at it, for instance, from a flow frequency perspective. In this case, what is the new transfer function? What is it? What would you say the transfer function is? Forget about the high frequency stuff for a second. Forget about the capacitors. So how do we do this? There are different ways of doing this. You can use the return ratio, for instance, for this guy. Use a pi model here, but this is source grounded, so it makes it easier. Pi model, scale that thing, and calculate the different parameters, right? So what is the parameter? If you calculate the parameters, we can let's quickly do some of the basic parameters for that source. So H infinity, right? First, H infinity for that source for M1 pi model GM. So what is H infinity? In other words, if this K goes to infinity, what does that mean? It means that this voltage at the input has to be zero, which means, and the current was zero anyway, and it will also mean that the current is zero even at high frequencies, because the voltage is zero. So there's no current through the capacitor. There's no current through here either. So what happens is that this current goes directly into here, and from a small signal perspective, it means that it's going directly through here, going into here. So small signal current going this way, I in, the small signal current cannot go through here. From small signal perspective, this is an open. It's a constant current, right? So current going into here, and that basically tells me what my output is. So what's my output? So if you think about this model, second.
Negative RF for I.
Negative. So this voltage, basically, I don't even need to think about that current anymore, because this current going through RF, this voltage being zero, tells me what this voltage is. Right? So this is zero. This voltage drop here, so this voltage becomes now minus RF IN. So H infinity is very simple. So what this feedback does, basically brings your overall transfer, ideally, if you had very large loop gain, it brings your trans resistance to RF, makes it minus RF. If you had large enough loop gain. Okay, so now if you wanted to calculate these two other parameters, you can calculate the T and H0, but let's not do it for now, just leave them here. So we can calculate them. And when we need to, we will. Let them sit there. But let's now start with some values. right? So let's calculate the, for instance, now let's start with an RF of 500 kiloohms, a large value. So let's start from small feedback, basically. If you start at 500 kiloohm, now what do you expect to see? You can actually calculate what your transfer function is. And if you look at the, let's say, a simulation. So let's look at the simulation result. It's on figure 6.4. So this is the amplitude plot, magnitude plot, and the time domain response, the step response of this. So what has happened? All of them have just applied feedback to this. I have peaking. Now if you look at it carefully, how much peaking do I have? Well, it's about, in this case, let's see, I have it written somewhere. 5 dB? 40. So about 44 or 5 dB of peaking, around 75 megahertz. So what has happened? The bandwidth has gone up. So the bandwidth was like 36, and it is definitely more than 75. If the peaking is happening at 75, the 3 dB bandwidth is going to be after that, right? So now my response looks like this. And the gain has gone down to minus 110 instead of to 110 dB ohm as opposed to 120 dB ohm. So now it looks like this. Right, it actually looks like this. The green curve. And this is about 4 dB with 500 kilo ohm of resistance. And your time domain response, if you look at it, now instead of this, you see something that's faster, but peaks. A little bit. Rings a little bit. So, is this acceptable? Well, it depends on what you're trying to do. If you're trying to make an amplifier to amplify, let's say, digital pulses, non-return to zero pulses, ones and zeros, this is probably okay. This is much better than that, probably. Because now it can actually, you get a faster rise and fall time, and this doesn't really matter if it's a digital pulse. If it's a D2A, the output of a D2A trying to settle quickly, then this could be a problem. So it really depends. But the main point of this is that you see that as soon as we apply feedback, and we will analyze this a little more, in more detail in a few minutes, but you saw this. You had a circuit that had 3 left half plane real poles. And you apply just one resistor to it, feedback. And now you're creating things that are clearly have complex poles. Okay, fine. And we've seen this. This is not the first time. We saw this when we were doing the analysis. We saw a couple of cases when we had the time constant in there. We saw that the poles would move when we were doing feedback. All right, fine. But now let's go a little bit further. Now instead of 500 ohms, let's go to 150 kilo. So let's change RF from 500 ohms to 150 kilo and see what happens now. If you do that, your gain will go down to about 102 dB at low frequencies, which makes sense. You're applying more feedback, right? So you're lowering the gain. And how about your frequency domain response? Now let's look at 6.5. So what you see here is that the amplitude now has, how much peaking does it have? It's about, I believe it's about 19 dB. It's a lot of peaking. And you have to look at the time domain response at 150. It's ringing a lot. Now it's doing this. Okay? Is this okay? I would be hard pressed to come up with an application where this is fine. Yeah. If you're trying to make something that makes a ringing sound, you can use it. But yeah. So now that's fine. But now let's go a little bit further. Let's go to if the next number we pick is, so this was 150, right? No, I'm saying this was 150, yeah. So now if you go to 116, 116, now look at it. It's on 116 kilo ohm, or f of 116 kilo ohm on 6.6. What do you have? This is right, starting to get exciting. Right? You have 53 dB of peaking. So this goes a little bit farther down. You have 53 dB of peaking. And look at the time domain response, the step response, which is on 6.6. It's an extremely slowly decaying sine wave. So it looks like it's still decaying, but very, very slowly, as you can see. So you are getting close to something, right? So now, instead of 116, now let's go to 112. If we go to 112, now, this is, be careful, just like I want to pay attention to a couple of things. The Bode plot, peaking, it peaks still, right? But how much does it peak to 112? Do I have the number? 38. So it's peaking less. So if you just were to look at the Bode plot, everything seems to be nice and dandy, right? No, I mean, it's peaking, but you would think that this is probably better than the previous case of 116. It's peaking less, not more.
If
On
we
the
don't
Bode
look
plot.
at the phase, right?
Hmm?
But if we ignore the phase plot.
Yeah, sure. But just like look at it. So what I'm trying to tell you, the lesson I'm trying to draw here is that a lot of people look at this stuff and they may say, okay, well, it doesn't look that bad. Well, the system can, you can actually have things that don't peak. And they are oscillated. Because if you look at the time domain response of this thing, now you have a exponentially growing sinusoid output. So how is it that the Bode plot doesn't even show it? What's happening? Well, let's look at this picture. A little bit more. If I were to break this loop, let's say somewhere, and at any point, if I apply if I break it, it is abstracted form, it doesn't matter where you break it, somewhere, and you apply some signal, Vx, let's say some sine wave, and let's say the loop gain, the sine wave comes back in phase, exactly the same. Let's say it comes back exactly the same phase, same amplitude. The second part is important too, same amplitude. Now, in that case, what would you say AF is, or T is? Minus 1, right? Because of this minus 1 in the definition. Somebody put it in there. But you have to deal with it. So when things come back exactly in phase, and exactly the same amplitude, AF or T would be what in this case? By the definition, because of the minus sign, it's going to be minus 1. So what happens with this transfer function?
Okay.
If you have a minus 1, it blows up. But it only blows up for an AF of minus 1. If it came back in phase exactly, but double the amplitude, for the sake of argument, what would you get? AF is what? Minus 2. Now if I put minus 2 in this equation, the transfer function is whatever, right? It goes A over minus 1, it goes minus A. This guy doesn't show that something strange is happening. And this may or may not, the second case, may or may not correspond to something bad happening. It's not necessarily something bad happening. And we'll see examples where it doesn't. Okay? So, but you see, you should expect the Bode, the closed loop transfer function to show any of this to you directly. What And they're two completely different parameters. And you can learn some properties of the system from the T that you may not learn from the H directly. Because only if this condition exactly occurred, that it came back in phase and in the same amplitude, this would blow up. And as you saw, in this example, when this became 112, this guy didn't go to infinity. In fact, you had less peaking than 116. But your time domain response was growing. So, what's happening? So, let's look at several different things when we are looking at this. And let's see what's happening. So, let's break this loop. Let's calculate the loop gain of this example. So, where would you break this loop if you were lazy like me and wanted to do the minimum effort with the assumptions that I have? Where would you break it? Any suggestions? I want to make my life as easy as possible, so I want to pick a place if I can. In general, you cannot, but I mean, if you take into account all the parasitics and everything. But in this case, we've simplified the circuit, so we can actually find points where one of the TI or TVs go to 0, and the loop is. This loop is actually unilateral anyway, because there's no signal going in the opposite direction here, because we have no capacitor.
On the input side of the feedback.
On the input side of the feedback, you mean here?
Yeah.
I could do it there, but then I have to do. But in this, if I break it here, both my TI and TV would be non-zero, right? Because I have resistance here. So when I want to determine the loop gain, of course, that goes away. Now, how about here? This is the place where I have an open. So if I put a current source into here, I get infinite voltage here, right? So whatever comes back to infinity, small signal model. So Ti is infinity, so I need to only worry about TV. So I can apply a Vx here and Vy. And if I couldn't, I have to do both, which is fine. We could. Okay, so we can determine this loop gain. Let's go determine this loop gain. And we have to pick a lot of. So let's see. So I know since Ti is going to be 0, my TV is T. So my overall loop gain is going to be basically, in this case, my TV F of S. So to determine that, first of all, again, it's a transfer function, right? From this input to that output, from this voltage. So I can use the methods that I know. So first I have to determine T0 or T0. What is the low frequency transfer function? What is it? So first I have to determine the gain from here to there. Now what's that gain? It's a so I have an Rm here. I have an Rf here and an Rs here. So it's a voltage divider between them. So it's an Rs over Rs plus Rm4 plus Rf. Okay, and then I have the three GM1R1s, GM2R2s, GM3R3s. That's my loop gain. It had a minus sign, but the minus sign cancels because of the definition of the loop gain. Remember, it's minus Vy over Vx. Because there are three minus signs, so there will be one minus sign left, and that one minus sign is cancelled with this. So this is my low frequency loop gain. So how about, now, if I want to determine the poles and zeros of this loop gain, how do I do that? How many poles, how many zeros does this loop gain have? This transfer function from here to this voltage to this voltage. How many time constants do I have? In
3 poles again?
3 poles again. Do I have zeros?
No zeros.
No zeros. Are they the same poles?
No. One of them is
No, one of them is different, right? So, which one is different? Which time constant is different?
tau in.
Tau in. So it's tau in prime. Tau 1 and tau 2 are the same. So this is basically C1R1, C2R2. But this one's the new tau in. So it's Cn times Rs parallel Rf plus Rm4, exactly. So, you know what a loop gain is? No. It's not that difficult. So you can look at this loop gain and see what happens. So let's look at the loop gain and see what happens. So I have basically now, and are they poles, the time constant, are they uncoupled or coupled? No. What do you think? They're still uncoupled, right? Nothing has changed. So there are three time constants, they're uncoupled, so my loop gain is basically T0, 1 over 1 plus tau 8 prime s, 1 plus tau 2, tau 1 s, 1 plus tau 2 s. So I know exactly my loop gain, what my loop gain is, right? Fine. What do we do with this? I know the loop gain. Let's evaluate. Now, the question is, I want to see if my transfer function has right half plane or left half plane. Or what are the poles of my transfer function? Are these the poles of the transfer function? No. What are the poles of the transfer function? Right. You remember we said the roots of 1 plus t of s should be the same as the roots of the delta, which means that these are the poles of the transfer function. So the roots of, so we say, of this are poles of h, or in this case z. Well, let's get h of s, the transfer function of the system. Right? This is generally true. So we have to evaluate whether 1 plus t of s has roots in the right half plane. So what is 1 plus t of s? So this is t of s. So 1 plus t of s is has a numerator which is basically 1 plus tau in prime s, 1 plus tau 1s, 1 plus tau 2s, plus plus t of 0, exactly, divided by these three. I want to determine the roots of this, which are basically the roots of the numerator. So I'm only interested in the numerator. So I have to expand the numerator. So what's the numerator? So I want to determine basically the equation I'm trying to solve, in a way, is 1 plus t of 0 plus tau in prime plus tau 1 plus tau 2 s plus, now the two-way product, sum of the two-way products, tau in tau 1 plus tau in prime tau 2 plus tau 1 tau 2, right? S squared plus tau in prime tau 1 tau 2 s cubed equal to 0. So the roots of this, if I have any roots with positive real values for this, my system is unstable. Or the locations of those roots of this will tell me what my system does. If you have things that are left half plane but still close to the j omega axis, then I have systems that are under them. And if I have things that are on the right half plane, then we'll have things that will basically exponentially grow, like you saw. So that must have happened, right? When I had an exponentially growing response from a linear system, what did I have? An exponentially growing sinusoidal response. I must have what? What can you say about it?
Right half plane.
More than, yes, right half plane, but we can say even more than that. You can have, what kind of right, can I have real right half plane poles?
Dimension.
Well, complex. They have to be complex. They have to have a pair, you have to have at least one pair of complex conjugate poles on the right, in the right half plane to get sinusoidally growing exponentially. Right? And this has three roots anyways, right? So you can easily say, no, that the third pole is going to be real. You get one real, two complex poles. Why is the third pole real? Because they have to come in, if it's complex, it has to come in pairs. Which means that you will have four poles, right? If you have three poles, two of them are a complex conjugate pair, the third one has to be real. Okay, put numbers in it, right? So if I put numbers based on the things that we had, I tell you what the numbers are. So you get something like this. You get 9.81 plus 6.49 nanosecond times S plus 13.7 nanosecond squared times S squared plus something 9.313 nanoseconds cubed S cubed equals 0. Okay. So how do you tell me whether or not it has right half plane poles? Does anyone know? If I show you something like this, what do you do?
Routh-Hurwitz.
Routh-Hurwitz method, right? Right. So in general, if I give you a polynomial of n order, right? What do you do? Can you calculate? Can you determine when the transfer thing is? No. Well, yes, you can, right? So there's this method called Routh-Hurwitz method. So it's a mathematical method. Basically, it was not invented by engineers. It was just like mathematicians were interested in algebra things. So it's a question of how do you determine surfaces? If I gave you one polynomial with some coefficients, how do you determine if it has right half plane roots with positive root? Well, this is what you do. So if the polynomial looks like this, so if polynomial is 1 plus, well, let's say a naught plus a1s plus a2s squared a(n)(Sn), you write the coefficients this way. You start with the highest order coefficient and every other one. So you write basically an minus 2, an minus 4, all the way to whatever, an minus something. Excellent. The lowest one, the lowest order one. And then you write the other ones underneath it, again, every other one. An minus 1, an minus 3, an minus 5, all the way. Okay. And you write, basically, this is first order, this is first, second. So you form a table like this, and this is what you do. You calculate B ends. So what you do, B is this multiplied by that minus this multiplied by that. So I'm going to write it here. So B is an minus 1, an minus 3 times an minus 3 minus an times an minus 2 and minus 3 divided by an. So this multiplied, it's like a matrix multiplication kind of, right? This by that minus this by that divided by this. Right? And then the next one would be, you always use the first row, first column, and then you multiply it this way. And that way. So the next one would be an minus 1, an minus 4 minus an times an minus 5 divided by an minus 1 divided by scale by this. So you get another set of coefficients, and then you do the same thing on the fourth row. So basically, you do it the same way for these two rows. And you go down. You get C's and D's, and so on. So I then just do a couple of numerical examples. On this. Move it down. Sorry, just like I have to find my. Alex.
Wikipedia example.
Okay, no, I want this is one particular example. Actually, I wanted to show something about it. Just, I mean, you can pick any example. There's something about this example.